Welcome. My lecture is on extra high voltage AC transmission. The contents of this lecture includes introduction, need for extra high voltage AC transmission, advantages, disadvantage of AC transmission, and power handling capacity and line losses of EHV AC transmission. The generation and consumption of electrical energy has been increased at a tremendous rate throughout the world during the past few decades, and this increases the need of higher amount of power transmission over long distances. So voltage levels, we have to increase the voltage levels for the power transmission. As per the current terminology, the transmission voltage levels are defined as high voltage ranges of voltages are less than 300 kV. Extra high voltage EHV voltages are in the range between 300 and to 765 kV, and ultra high voltage ranges is greater than 765 kV. The requirement or need of EHV AC transmission includes the following points. The increase in size of generating units. In present scenario, the size of generating unit is continuously increasing. To fulfill the continuously increasing the demand and growth in load, and to reduce the investment cost per kilowatt, the size of generating unit is increased. The AHV and UHV ranges are utilized in power transmission over long distances due to their technical and economical feasibility. And the second point is the need of EHV transmission is the pit head steam plants and remote hydro plants. Usually one of the major costs involved in thermal power plants is the transportation of coal, and the pit head steam plants are the super thermal power stations situated near the coal fields as the transportation cost is reduced. So these are known as pit head steam plants. And similarly, we can say that remote hydro plants depends on the sites characteristics, the favorable characteristics of the sites, that is the availability of water, cheap land and labor, etc. The hydro plants are also situated near at remote areas. So the power transmission, higher amount of power transmission over long distances, we have to go for EHV AC transmission. Line losses is reduced with increasing the level of voltage for power transmission. As the same amount of power going to transfer at higher voltages, the current is reduced, and for reduced current, the conductor requirement is also lesser diameter conductor is required. Hence, the resistance of the conductor is reduced. Hence, so the losses, I square R losses, ohmic losses in transmission line is reduced. So we can say that the transmission efficiency is increased at extra voltage transmission. The size of conductor is reduced with the reduction in line current, which also decreases the volume of conductor and the cost of the conductor. The power transmission capacity is proportional to the square of the operating voltages. As the voltage level is increasing, power transmission capacity is increasing. It is economical with EHV AC transmission to interconnect the power system of large scale. With increasing the transmission voltage levels, the interconnection of power system to the large scale power system is economical. And so we are going to choose the extra high voltage AC transmission. The advantages of EHV AC transmission includes the following advantages. The increasing the transmission as the losses in the EHV AC transmission is reduced. Voltage regulation is improved. We can say that the resistance of the conductor is reduced, so the voltage drop in the conductor is reduced in power transmission. So voltage regulation is improved. Lesser value of conductor volume due to the lesser diameter required due to the lesser current flowing through the conductor. Increasing the power transmission capacity, as power transmission capacity is proportional to the square of the voltage of transmission voltage. So we can say that power transmission capacity is increased. Installation cost of transmission line per kilometer decreases. The surge impedance loading is proportional to the P square by Z0. Z0 is the surge impedance, and that is given by root L upon C. L is the inductance, C is the capacitance of line, which SIL increases, which indicates the power transfer increases with the increasing the transmission voltage level. Large scale interconnection of power system is possible with the EHV AC transmission, and flexibility for future expansion of power system in case of increasing the power demand in future. It is flexible for EHV AC transmission. Lesser right of way, we can say that the lesser number of circuits are required to transfer the same amount of power in case of 400 kV, 750 kV. We can say that 750 kV will require lesser number of circuits as compared to 400 kV for the same amount of power and for same distance. Reduction in losses. It is already discussed that the losses, I square R losses are reduced due to the lesser in current and lesser diameter of the conductor. The drawbacks in disadvantages of EHV transmission includes the corona loss and radio interference. As the conductor diameter is reduced and voltage level is increased, so the corona visibility, corona visibility is more for the lesser diameter conductor, and it increases the corona loss, and intensifying radio interference is also produced in case of EHV transmission. The insulation requirement, we can say that the insulation requirement is going to be increased as we are going to increase the transmission voltage level. So larger space between conductors and between supporting structure and conductor is required in case of EHV AC transmissions, and this fact produces the heavy supporting structure for the power transmission, and also it includes the erection difficulties of these heavy supporting structures. The current carrying capacity is reduced as the voltage level is increased, and Ferranti effect. Ferranti effect is the effect which shows that the receiving end voltage is greater than the sending end voltage at light load condition due to the shunt capacitance of the transmission line, and Ferranti effect may be much more severe in case of EHV AC transmission in case of light load condition. The environmental and biological effect. The EHV lines generates more electrostatic effects as compared to HV or normal voltage, which are harmful to the human being and animals. And suitability consideration is also another disadvantage or drawback of this EHV transmission. The cost of transformers, switchgear equipments, protective equipments increases with the increase in transmission voltage. Power handling capacity and line losses. As we are assuming that the line resistance and such capacitances are neglected for the transmission line, the power transmission Then the power transmission through the transmission line depends on the voltage magnitudes at the sending and receiving ends, that is noted by ES and ER, and the phase angle difference in between these two voltages, ES and ER, that is delta. And another factor is another point is the total positive sequence reactance X per phase of the conductor. And then the power transmission through the transmission line is given by P is equal to ES ER sine delta divided by L into X, where L is the length of the conductor, length of the line. So P is equal to ES ER sine delta L by X by L into X. At a unity power factor, the current through the connected load P is given by I is equal to per phase current. I is the per phase current. I is equal to E sine delta divided by root 3 L into X. Here root 3 is indicating for per phase current. Root 3 is indicating here per phase current. And the total power loss in the three phase is given by P is equal to 3 times I square R. R is the resistance per phase per kilometer, and L is the length of line. So total power loss is given by 3 times I square R into L, and it is given by putting value of I, it is given by E square sine square delta multiplied by R divided by L into X square. Therefore the percentage power loss can be calculated. Percentage power loss is given by ratio of power loss divided by power transfer through the transmission line. That is the percentage power loss, and it is given by 100 sine delta multiplied by R divided by X. For delta equal to 30 degree, for delta equal to 30 degree, the percentage power loss at different system kV, system voltage, transmission voltage, that is 400 kV, 750 kV, 1000 kV and 1200 kV, and at different line length in kilometers, 400 kilometers, 600 kilometers, 800 kilometers, 1000 kilometers, 1200 kilometers. The percentage power loss is given as 50 by 10.55 for 400 kV, that is equal to 4.76, and for 750 kV it is equal to 2.5, 1000 kV it is equal to 0.78, and 1200 kV it is equal to 0.554. It is indicating that the percentage power loss is reduced with the system voltage increases. It is 4.75, 76, 2.5, 0.78, 0.554. And the power transfer through the transmission line is given by P equal to 0.5, as sine delta is equal to 30 degrees, so sine delta is equal to 1 by 2. So here is 0.5 E square. E square is the E of ES and ER. E square is the voltage magnitude of receiving and sending end voltage, divided by L into X. L is the length of conductor, X is the reactance of conductor per phase per kilometer. That is given in megawatt. So power transfer through the transmission line for 400 kV, 400 kilometer line is equal to 760 kV, 750 kV for 400 kilometer line, that is equal to 2860, and for 1000 kV 400 kilometer length of line it is equal to 6000, and 1200 kV 400 kilometer is equal to 8625. As the line length is increased 400 kilometers, 600, 800, so the 400 kV system voltage, the power transmission capabilities or power handling capacity is going to reduce with the increasing the length of the transmission line. It is similar for 750 kV also, 2860 1900. It is going to reduce up to the 950 for 1200 kilometer length of transmission lines. Similarly for 1000 kV also and 1200 kV also. And it is clear that as we are going to increase the system voltage levels for a fixed length of transmission line, the power transfer capability or power handling capability is also going to increase for different length of lines. It is clear. So some conclusions can be drawn from this table. The power transfer by one 750 kV circuit is equivalent to 400 kV circuits line. One 1200 kV line carry power equivalent to 3 750 kV lines and 12 400 kV circuits. It is clear from the above table. The power handling capacity is inversely proportional to the length of line. It is also cleared through the table. As the conductor size is reduced, this will lead to higher corona on the conductors and intensifying radio interference level due to the smaller conductor. The percentage power loss remains independent on the length of the line, as it is clear from its formula that length of line is not percentage power loss is not depend on the length of the transmission line. The percentage power loss decreases with the rising the transmission voltage. It is clear in table also, and this is the important. This can be the important criteria for the selection of transmission voltage levels. Thank you.